Okay, can everyone hear me? Just respond in the chat to say yes. We're gonna give this another go. I'm not quite sure what happened in the last video. I'm guessing that, does anyone know why the last video would have been taken down? Error, probably. It said something about copyrighted audio. I'm like, I don't know what you are talking about. I'm defining math terms. Like, math is not copyrighted. But anyway, back to where we were. P series converges if P is greater than 1, diverges if P is less than equal to 1. And if P equals 1, it's a harmonic series, diverges. So this follows our rule right here, which actually, you know what, I'm going to label that. I'll do green for theorems because, I don't know, I heard that your mind remembers things better if you associate it with the color. So P series converges if P is greater than 1 and diverges if P is less than equal to 1. We will call this the convergence / divergence of a P series. Star. All right, so that's a P series test. And then you were asking the difference between that and the integral test, I believe. So the integral test is very, very different. Let's see. Oh, I understand. So the reason you're probably confused is the next part right after you read the kind of definition and generic outline of a P series. The next part immediately following that is the proof of that, which uses the integral test to prove for a P series, which the integral test is very useful, but honestly, you should already know how to do it. If you remember improper integrals, it's basically let's see what we got. I've got it written down word for word. So the series converges if and only if the improper integral also converges. So the integral test is we didn't use that in sequences, but the integral test is very simple. It's basically, so I actually didn't write this down, which I will now correct my mistake, but this should be where k equals 1, k equals 1. You can't just do it from k to infinity. That really wouldn't make much sense. But basically what the integral test is it's saying that if the improper integral with the same bounds, 1 to infinity, of 1 over, and you would have to put it in terms of x. You don't really have to. You can use k as a variable if you want. I think that's a bit of an anarchist move because k is not a great variable because k is always a constant, but you do you. So we got the integral 1 to infinity dx over x. Obviously that's the harmonic series, but this right here is actually kind of a tricky thing, but that you should pay attention to, because let's think about this. What is going to end up being the integral of that, right? So we've got, let's see, we all know that 1 over x is the reciprocal function, and when we integrate that, that's going to give us the absolute value of a natural log, right? So we're going to have natural log absolute value of x from 1 to infinity. And for future reference, if you're going to do this on a test, don't forget to, I'm not going to do it because I think you guys already get the idea, but limit, so this is b, it's a to b, right? The integral from a to b is just 1 to infinity. So a lot of professors, they want you to do it this way. They want you to say, as b approaches infinity, and then just put b in there instead of infinity. And then most professors, I'm assuming, would want you to put that every step of the process for the integral test, or even just for regular improper integrals. That's kind of a contradiction, but regular improper integral. But anyway, this would end up working out to natural log of infinity minus the natural log absolute value of 1. And remember, we don't need a plus c because this is a I'm totally blanking on the word. I'm being dumb right now. Well, this is an integral where they already give us the values. I'm blanking, that's my bad. Which anyway, this would work out to natural log of infinity is just infinity. Natural log of 1 is 0. This is equal to infinity. Indefinite integral, that's what it was. Indefinite. This is a definite integral. That's why you don't have a plus c. But anyway, that would diverge, if you remember, from improper integrals, because pretty much an improper integral will converge to any value other than a non-real value or an infinity. So this would still diverge for this. So this integral test works quite well for series, but do you guys remember sequences? For a sequence, though, we don't get this result. For a sequence, a harmonic series, or just a harmonic sequence, I guess, 1 over x, right, as a sequence, that is going to converge to 0 as x approaches infinity. But for series, that's different. I'm sure you guys are probably wondering why, and there's actually a really cool proof for it. And since you guys are all quarantined at home, I'm gonna take the time to explain to you guys why this stuff works, because I don't think we do a lot of proofs in Calc 2, but this one is definitely one that you should know and will help you understand the concept on a deeper level. I mean, I genuinely enjoy this proof. Let's see if I can find it. Yes, here it is. Yes, here it is. So real quick, before I start this, does anyone need more time with what's on the board? I don't know if you guys are taking notes or not. If you don't need more time, please let me know in the chat. Otherwise, I'm about to erase what's currently on the board. So kill it, erase it, or keep it another minute. Anyone? Perfect. This is a democracy, y'all. If you don't respond, then her opinion is going to stay. And that kind of becomes a dictatorship if you have a democracy where only one person votes. Is that a dictatorship? Man, I'll have to ask Haley that. That's her thing. Politics is her thing. I just do numbers. Okay, so for this, we're proving that here, I'll show you guys some proof format and everything. This is not going to be a formal proof. It's kind of it's going to be a informal proof that I think there's another video on that you could probably find something very similar to this. I kind of use a variation of the textbook and the other textbook in the other video. You can just search proof harmonic. Hold on, gotta hold the pencil. Series diverges. Or actually, you know what? If you're searching it online, no, just I was gonna say prove like present tense, but that's probably fine. Yeah, if you just search this up online, there will be a more detailed. I'm just gonna go over a general outline and kind of explain it as I work through it. So, yeah, this is such a cool proof. I love this one. Am I still alive? Not taking me down this time. Good. So let's take this right here. And you know what? You guys aren't really taking a proofs class, but you write that before you do a proof. So, and then you draw a little square and shade it in when you're done to let them know that the proof is over. But I don't know if there's any math majors in here. I'm just figure I would give it the benefit of doubt. Or maybe some of you are interested in this. I don't know. Okay, so 1 over k from 1 to infinity. So that's going to give us, let's see what we got here. 1, right? For k equals 1, we're going to have 1. This is a series, which means we're adding all the terms. We're going to have 1 over 2 plus 1 over 3. This is going to get redundant soon. Plus 1 over 4 plus 1 over 5. But it does have a point. Plus 1 over 6 plus 1 over 7 plus 1 over 8, blah, 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 as it approaches infinity. So now, let me see what this is real quick. Yeah, this one's a bit of a pain, but what do we define S as? Well, anyway, there's a set S, we'll call it, and what's going to be similar to this one, but it's actually going to be, oh, good, I labeled it. Okay, never mind, I'll explain it better. Here we go. So we're going to take this one, bring it down into our set S here, right? So then S, we're really just condensing right here. That's a 1 plus, by the way. I'm trying to write good, I really am. But anyway, where was I? Let's see. 1 plus 1 half plus 1 fourth. So now this part right here is kind of where this gets a little bit tricky. But it's not horrible. It genuinely isn't. So this right here, we'll take this 1/3. No, I don't like that. That's kind of gross. And we'll circle this just for clarity. So 1/3, we'll put that 1/4 in there. And then, who's good at fractions? Can anyone, this is real tricky, y'all. Can anyone do this difficult problem right here? 1/3 plus 1/4. What is it? Fractions. Well, anyway, this might take a little bit longer than it needs to, and we don't really need to cover it. I don't know. I mean, nah, this is first online session. If you guys want me to do a proof, I'll do it in a separate video. Hey, look at that, you guys responded. But I'm gonna do the proof in a separate video. This is a little more complex and it needs to be in a little bit theoretical. And I know a lot of you are engineering students and don't really need to know the hypothetical math. But if you do want me to do a proof of this in a separate video and a shorter one for y'all, just let me know, because I don't know, this just seems like it might take a lot of our time. I was looking at it thinking that this was it, and then I realized there's a whole backside to the proof. So that's probably I don't have a whiteboard real estate, the dry erase real estate for this proof, but I'll do it on a separate video. So geometric series. Oh, and by the way, just general properties of series, they work like integrals. Like if you have the integral of -1/x, it's equal to negative integral of 1/x. Same deal with the series. Like they react the same way to scalar multiplication and addition and subtraction that an integral would. Oh, here we go. This is actually pretty fantastic. This is one of the more useful things you'll learn in this entire unit. So this right here is the test for divergence. Test for divergence. It's a theorem. So it states, dang it, I said I was going to do theorems in green. I'll do it. I can leave the caption green and then I'll just leave the actual theorem part. Or I can leave the caption blue and make the theorem green. There we go. The trick, by the way, to improving your handwriting, 4-point hold like that. 1, 2, 3, 4. 4 points of contact, y'all. I'm gonna have pristine handwriting by the end of this quarantine. Divergence. So the infinite series a lot of math books do this. I never really understood why, but I guess it's just for clarity. The infinite series k equals 1 as it approaches infinity for a sub k diverges if limit as n approaches infinity for a sub n does not equal 0. But so the corollary, so to speak, for this theorem is that we know that if the infinite series k equals 1 as it approaches infinity for the summation a sub k, or series a sub k, diverges if limit n approaches infinity for a sub n does not equal 0, right? So then you guys are probably like, well, what if it does equal 0? Does that make it, if it does not equal 0, then it diverges. So what if it doesn't equal 0? Does that make it converge immediately? No. So the corollary and technically the second part to this theorem is that if limit as n approaches infinity for a sub n does equal 0, ready for the most anticlimactic ending here ever? This is just, they put this in here just to troll you because you're about to think, oh, then if it diverges. I'm getting ahead of myself or something. I need to slow down. I just got totally lost in my own thought. Yeah, divergence of a sub n doesn't equal 0 if limit. Okay, here it is. If limit a sub n, yeah, okay, my bad. That was me being dumb. But if limit as n approaches infinity for a sub n does equal 0, then it's either converges or diverges. And basically that means that you're back where you started and you don't know. But there are a lot of ways to find. There are tests for convergence to show. So if we do the test for divergence and it equals 0, then we've already done half the test. So now we have to do the convergence test and see if it converges, if it does converge or diverge. And that's where I'm pretty sure we just introduced this in class, the limit comparison test for infinite series. That's where that comes in, and also the direct comparison test, which you guys might remember both of these from sequences. We did some very similar things in sequences, not identical, obviously, but very similar. We kind of just touched in on it. Limit comparison test, definitely, but there's a few little nuances here, and I have some very helpful tricks that'll make it a little more smooth sailing. Okay, so two infinite, here's a theorem. I'm just going to read this one, see if it's worth, I'll read it out loud in case anyone wants to hear it. If two infinite series are identical after a certain term, then either both series converge or both series diverge. If both series converge, they do not necessarily have the same sum. Yeah, so convergence doesn't mean that they have the same sum. Identical after a certain term. Yeah, because their beginning is going to be different. And, you know, like, what is that old saying? There's no infinity does not always equal infinity. Like, there's a really cool math symbol for this. Wherever my rack went, there it is. Yeah, so for the universal set of infinity, we'll call it U, and we'll just call that the set of all infinities, right? Infinity is not equivalent to every variation of infinity. It's not logically equivalent. Car, yeah, I live right by the road. That's Stadium Village. It's actually a pretty nice place if you allow it to be, but there's definitely always noise. It's very difficult to sleep. I have two pillows, one for under my head and one for over it. But anyway, back to math. Okay, yeah. So this theorem is actually a generalized introduction into the comparison test right here. It's saying if two infinite series are identical after a certain term. Yeah. So this is like less than, equal to, greater than, equal to. You guys, this is some powerful stuff we're about to learn. So partial sums, blah blah blah. Where is the good stuff? Sum and difference of convergent series. So again, when you're adding and subtracting series, it's going to be pretty much the same rules as integrals. They are, like just basic addition, like here. So So like if you have here, this is just when you're working with these types of things. And a lot of this, by the way, guys, like make sure to really know your exponent rules well, because this stuff, when you're working with geometric series, if you know basic algebra, like the rules of how exponents work, adding and subtracting exponents, and how you can break apart, like, so you had e to the fifth, you can write that as e to the third times e to the second. So really, if you're just, good at algebra, if you just paid attention in high school, then this shouldn't be too bad of a unit for you, especially after coming out of integration. This is mostly theory stuff. Like a lot of this is kind of hard to wrap your mind around, but after you do, I don't know, say north of 30 types of problems for this, it'll probably start to make sense and you'll kind of understand the theorems and stuff. It really helps if you can graph, if you have access to stuff that like if you have if everyone here should have access to the internet, so use Desmos. And I don't know if they can actually compute that, but I would double check. I mean, it would be worth looking into. Or really you can kind of just draw it out on your own by hand, like, it's just going to be a summation. But besides that, let's see. And same with this is just, addition, subtraction. Doesn't really matter. It works both ways. So, like basic rules of math, they still apply. This stuff right here, this how it's kind of laid out stuff, this is more important in classes like linear algebra and differential equations. If you guys are going to end up taking those, you'll learn what a linearly independent set is. You'll learn like the basis, stuff like that, and it'll kind of be a lot of the theorems for those types of classes are going to be based on the calculus stuff. If you can really learn this stuff right here, then you will thrive in like a class, say like linear algebra. Because it's not the same content, but it is a very similar style of learning from the summation and series moving into linear algebra, and then the integral half of calculus 2 is definitely like the kind of introduction to differential equations. So if you do well in like in Calc 2 in the integration section, you're probably going to have you're going to have an easier time than most would, than someone who didn't do well in integration, that you would have an easier time than them in differential equations. But this stuff right here, like infinite series, if this is what you're thriving in, then linear algebra might be a class that would interest you. Like it's very, linear algebra is a lot more conceptual, like this stuff. But just figured I'd throw it out there because I know registration is going on right now. And maybe, who knows, maybe if you enjoy this stuff, it'll drive you to be a math major, and you really don't have a reason to not do this type of stuff because you're all locked in your homes, just like me. So, I mean, you might as well get some math out of it, like get something out of it. Averages, no, we don't need to go into that. Integral test. Integral test we kind of briefly went over already. So comparison test for convergence. We already, oh, that's interesting. My book has it as it has the direct comparison test in it before a limit comparison test, which I'm going to go into both. Actually, what is 544? Yeah. So we'll wrap up just kind of going into some, this is really powerful stuff right here. Like this is a comparison test. This will be definitely something that if you understand this well now, then an A on the test is very attainable, because this is going to be pretty much all of infinite series. It's just going to be some variation of a test that you'll learn for comparison, of convergence, divergence, et cetera, et cetera. I think I already kind of went into the ratio test in one of my sessions, just kind of introduced it because someone asked a question that was very relevant to it that involved a factorial. But For now, we're just on comparison tests, which again, this is very, very good stuff. So if you're taking notes, now would be a good time. So let's start with the comparison test for convergence, because I kind of just left you guys on a cliffhanger with the test for divergence there, which if you remember correctly, it's a limit as a sub n approaches infinity, as n approaches infinity for a sub n. If it does not equal 0, then it diverges. If it equals 0, then it converges or diverges. So this is part 2 of that. This is the comparison test for convergence. So this right here is actually pretty great, because it's going to answer the question that we asked when we left, which is, how do we, we said that if it equals 0, then it either converges or diverges. It doesn't necessarily do one or the other. We don't know what it does. So this is a good second step to do. Like a good process for when you're first starting out with these types of problems would be to probably try the limit, test the test for the general series test for divergence. If it does not equal 0, then you at least immediately know it diverges and you don't have to do any more work for the problem. But if it does equal 0, then this would be your next step. And as you do more of these types of problems and become more fluent in the math, you can probably start moving away from using the test for divergence for every single type of problem, because you'll, understand the content better. But just as a general safety net, I would highly recommend starting every problem test for divergence, unless it's a very obvious type of problem that has a very obvious form, like say a p-series. You don't really need to do the test for divergence. It'll work for it, by the way, it will. But a p-series, a geometric series, which we're going to kind of touch in, but this is, I feel like this should be taught before that, but that's just my 2 cents on the matter. I mean, I don't know, why go into specifics early on when you can go into general ideas early on and then build on the small ideas as you go? It's just my 2 cents. But back to math, if 0 is less than, no, just less than, not less than equal to, 0 is less than a sub k is less than equal to b of k. That's a b. My apologies. My handwriting is still a work in progress. B sub k for all k. Again, you'll see this type of proof wording here in higher math classes, which is why I highly, highly encourage that you read the textbook now and kind of get into the habit of it, because no one's going to be telling you to read the textbook next semester. And if you get used to this type of wording, upper level math classes beyond calculus 2 will be a lot easier. Math, it does build on itself. And you got to be up to date. And then eventually, the better you get at it, it's not like you're learning individual letters, but instead it's like you have a vocabulary of terms and math knowledge that you can rely on. Also converges. And that's for all k, for both of them. So this right here, it's the comparison test for convergence. And basically what it states is that if a sub k is greater than 0 and is less than equal to b sub k for all k, and b equals 1, and for the series from 1 to infinity for b of k converges, which is greater than or equal to a sub k, then the series that is less than equal to b sub k, a sub k, is also going to converge. Now this is let me see, I might have a good graph for this somewhere. This is actually you know what? There's like something very specific that I have in mind that I can pull up online real quick. Let's see. Comparison test for convergence graph. Here, okay, this is what I was looking for. So, do I have enough room here? Yeah, I'm gonna change colors though. Keep it lively, interesting. Life only gets boring if you let it. So known comparison function, given function. So we'll call this, I don't know. So we'll call the given function f of x, and we'll say it looks something like this, right? Kind of tapering downward there. And then we'll say the function that we chose to compare it to, we'll call that, say, g of x. And this is obviously, this is going to be b sub k in this situation, b of k, and then f of x is going to be a of k. So you can kind of see, we'll say this is the part where it starts right here, and we'll shade in all of this because obviously it's a series, so it's going to be representing an area. And remember, g of x is also encompassing all of f of x because it is greater than or equal to it. So this right here, we're saying if g of x converges to a point, then f of x also must converge. And that is because when you think about a summation or an infinite series, right? Like here, there's a really cool picture for this too. Infinite series box. There's like a box analogy. You'll probably see it in your textbook, but it compares how an infinite series can be similar to like a winding box. Like if you know the Fibonacci sequence, it's very similar to that. Yeah, something like this, kind of neat. Like cut this into force. We'll just say, just let this kind of be a visual representation of what an infinite series would look like. And we're just going down, cutting each little box in the corner here into more fourths. And as you can see, we'll say this corner right here is the beginning. The idea of an infinite series is for it to eventually become some number area type deal that the series will converge to. So it's like it's saying that for the series it won't grow infinitely. Like a convergent series will converge to some value with the area. We'll say this is the starting point of the series, it's the finish, with the area, this representing where it converges. So I think we're almost out of time, but we can real quick before I teach here in the chat, guys, while I'm erasing this, would you guys rather do geometric series or the limit comparison test? Actually, you know what? I'm overriding this. I'm using a veto. We're doing geometric series because you guys already know what limit comparison test is. And we'll go over it next time as well, but I really want to touch in on geometric series because that is something that you've recently learned. So let's see if we can get just a general, I'm just going to lay out the general format of what a geometric series will look like so you can kind of learn to recognize it. And again, guys, I'm only going to be doing this probably twice a week, but please feel free to message me through the group chat for anything you may need help with. And remember, like, the textbook is always going to be your best resource. I mean, if you can learn to read a math textbook, there really isn't a whole lot you won't be able to do. I would highly, highly, highly recommend learning to be able to read math type writing. It will be very useful. That's my roommate. All right, geometric series. So a geometric series can be in the form, this is where I was talking about with those exponent rules. It can be in the form like this, k equals 0 as it approaches infinity for a r to the k. But this is also equivalent to the secondary form you can write it in, which is k equals 1 as it approaches infinity for the function a r to the k minus 1. So right here, these are the same deal. These are both called a geometric series. Where's the sharp point? There it is. Yes, we love math. Okay. Geometric series. This, that. Let's define some terms here. Let's say what A is. So A is some constant coefficient, which means you can put it out here if you want, but you don't really need to. So we'll say this is a geometric series with a little side note, a little condition here, when A does not equal 0. Because obviously if A equals 0, then no matter what we multiplied there, we're just going to get 0. And that doesn't really work. But let's see. Okay, and then another definition here for just a variable r. So r is the ratio. And you guys might remember this from pre-calculus, because I think a lot of high schools teach this type of math in pre-calculus. I'm sure you guys remember like geometric series and arithmetic series. You definitely learned that in high school. Ratio r is any two real numbers Oh, my bad. This is just an extra note here. But yeah, you guys know what a rational number is. I thought it said something about integers. That was my fault, but let's see. So you guys probably just want to know at this point how to find out if it converges, right? So I'll kind of skip to the more interesting part. You probably all have that down now. So I'm going to erase it because we're running out of time. So series convergence test. For k equals 1 as it approaches infinity. For a times r to the k minus 1. And this is, if you use the textbook, you'll see a lot of k minus 1. Not too many in the form of just to the k, unless it's trying to trick you, which it does in a couple of the examples. But it's interesting and you'll learn from it, so allow it to trick you, I guess. Because I don't know if it's fair to call it a trick, it's just you don't understand it at that exact moment. Converger and its sum is, let's see, equal to a over 1 minus r. And this is convergent if I was going to write out that whole word. If the absolute value of r is less than 1. So it converges if it's less than 1 and diverges if greater than equal to 1. For the absolute value of r, it diverges if that's the case. Okay, that's pretty much everything you guys have learned up to this point. You can review the limit comparison test. I'll go more in depth and do comparison tests in the next lesson. I'm sure this was kind of sporadic. I just kind of wanted to give this whole quarantine thing a go. I mean, might as well still try and keep what's going on. But if you have any suggestions for how I can improve these sessions, anything you would like covered in the next session, just put it in the group chat. I mean, I would rather you guys be honest with me and tell me what I can do to help you learn this stuff the best, because I'm sure that you are all really stressed about having to take Calculus 3 online or Calculus 2 online. That's not really what you signed up for. But we can make the best out of the situation. Just let me know. And I'm going to end the stream on that note. Have a good day. Wash your hands. Be safe, y'all.